Hi sir, so in this video I will demonstrate about different circuit design by using VHDL programming and how it works. So this is part 1A. Part 1A in mini project is just a simple VHDL code which copy from the lab sheet and program it on the Altera board. So in this part the circuit design is very simple. So if we turn on any switches, the corresponding red LED will light up. So let us have a try. So I turn on all the switches and the corresponding red LED will be turned on. And when we turn off the switches, the LED will go light up and light off. Okay, that's all from part 1A. Thank you. So in part B, part 1B require the student to design the light chaser system. So the default clock frequency of Altera board is 50 MHz and it is too fast ratio for the user to see the changes of the light chaser. So I had divided the 50 MHz to the smallest frequency so that we can observe the changes of the light chaser on the Altera board. After calculating for the bits, 25 bits of the counter is counted and it is used in the part 1B. So after we combining all the modules to the top level, it actually will form a light chaser from right to left on the Altera board. So this one is the reset button, which means when the reset button is on, the light chaser will stop functioning, and when it is off, the red LED will form like a light chaser from right to left. Yeah, so if I turn on the reset button again, the light chaser will stop functioning. So that's all from part 1B. So in part 2A, the students are required to design a hardware of sequencer shown in the figure here. So this circuit design is actually performed as a linear feedback shift register which can generate random pattern of bits. So this one is the last one is the reset button, and this one is the start button, the first one. So when the start button is being pressed, the system will operate and start generating random combination of bits. Yeah, the system is start generating the random combination of bits. So if you want to clear the bits, we can just turn on the reset button and the system will stop operating. So if you want to generate it again, we can just turn off the reset button and raise up the start button and the system will start generating the random bits. So this is what we call linear feedback shift register. That's all for part 2A. Thank you. For part 2B, since we are going to use propagation delay to create a circuit design, therefore the circuit is not synthesizable but only can be observed through the simulation result. In this part, we have two types of D flip-flop because of two different propagation delays, which is 90 nanosecond and 150 nanosecond. So in this part, I designed three modules, which are D flip-flop with 90 nanosecond propagation delay, D flip-flop with 150 nanosecond propagation delay, and top level module. So for the D flip-flop with 90 nanosecond and 150 nanosecond propagation delay, it is almost the same as the D flip-flop in the part 2A. So the only difference I have made is here. The Q will only take the value of the input after 90 nanosecond propagation delay, and same goes to the D flip-flop with 150 propagation delay. The changes of the input will not actually be instantaneously shown by the output, but will only shows after specific propagation delay. So we move on to the top level module. Yeah, for top level module, this part actually is used to declare the component of the modules that we want to connect to. So this part is create for connect the input to the output of the ports by using the signal that we have been declared and these other signals. So this part is actually for XOR gate operation. For here, I assign three output signals since we have three XOR gate. Yeah, so I assign this as the first one of the XOR gate as A, second one is B, and third one is C. So we look for the A1 first. The A1 is S1 connect XOR with S0 and XOR with S2. So the first one S0 XOR with S1. And then XOR with S2 again. So this form the XOR gate 1, and the XOR gate 2 is the S1 XOR with S3, S1 XOR with S3, yeah. And then we look for the third XOR gate. Third XOR gate is S2 link with XOR with S3 and S4. S2, S3, and yeah, S4. Yeah, this shows this. Yeah, this code shows the XOR gate here. And so for this, for the start input, this one start input, it basically used for kickstart the system so that the system can be run. So move on. This part is, so the rest of the part is for the interconnection of the D flip-flop and the XOR gate to complete the circuit, which show in the part 2b, yeah, here. And now we are going to see for the simulation result of this propagation delay. So this is the testbench codes for the D flip-flop with 90 nanosecond propagation delay, and I will start running the simulation result. As we can see here, the D input is given here is 200 nanosecond to 300 nanosecond. So when there is a rise in input signal which is set 205 nanosecond, only then the D flip-flop with 19 nanosecond propagation delay will be active. It's because it sends a high input only at rising edge here, which is 205 nanosecond, and it has to wait for 90 nanosecond to show the output since it had a 90 nanosecond propagation delay. So now we can see here, yeah, only at 295 nanosecond, the result of Q output will only shows out here, yeah. So this is the simulation result for D flip-flop with 90 nanosecond propagation delay. And now we are going to move on to the D flip-flop with 150 nanosecond propagation delay. And so this is the codes for the test bench codes for the D flip-flop with 150 nanosecond propagation delay. And same, we're going to run the simulation. Okay, so same as just now, the input given is also from 200 to 300 nanosecond. So like what I said just now in D flip-flop with nanosecond propagation delay, when there is a rise in input signal which is at 210 nanosecond, only then the D flip-flop with 150 nanosecond propagation delay will be active. So the system will only sense at a high input at rising edge, which is 210 nanosecond, and it has to wait for another 150 nanosecond to show the output since it has a 150 nanosecond propagation delay. So we can see here it sends the rise input is 210, and then only then at 360 nanosecond the output of Q will be shown up. So yeah, this is the simulation result for the D flip-flop with 150 nanosecond propagation delay. And then we will move on to the top level module. So this is the testbench codes for the top level module. So in this module, we'll run for 3 types of tests here. The first test is to run the simulation at clock period of less than 90 nanosecond. The second test is in between 90 nanosecond and 150 nanosecond. And the last test is above 150 nanosecond. So for the first test, I will be used for the clock period at 30 nanosecond. So I'll run the simulation first. Okay, so we can see here my start goes high for 30 nanosecond, but the D flip-flop basically does not have any change even though I give the kickstart value, but due to the short clock period, it is insufficient to actually load the start input into the combinational D flip-flop. Since the clock period is too small, therefore there is nothing changed on the output. So we will move on to the another test. So for another test, I've decided to use the clock period at 100 nanosecond. Yeah, so we run the simulation first. Okay, this is the simulation result for clock period of 100 nanoseconds. So I will open up the file I've said before. Okay, so when the system is given input high at the rising edge of the clock, which is at 150 nanosecond, only then after 19 nanosecond propagation delay, then the output will show up, which is at 200 nanosecond. So 240 nanosecond. So 240 nanosecond minus with 150, so we'll get 19 nanosecond propagation delay. Yes, but since the clock period of 100 nanosecond is still less than 150 nanosecond, therefore the D flip-flop will with 150 nanosecond propagation delay doesn't work again. So we'll proceed to the last test. So for the last test, I've decided to use the clock period at 200 nanosecond. So I simulate again. Okay, and again I will open out the file I said before. Okay, so this is the simulation result for the clock period at 200 nanosecond. So based on the lab sheet, the system will run for 90 nanosecond propagation delay first, then followed by 150, 90, 150, and the last 90 nanosecond propagation delay. So as expected here, the simulation shows results start from 90 nanosecond, followed by 150 nanosecond, followed by 90 nanosecond, 150 nanosecond, and 90 nanosecond. So for the first D flip-flop, which is it will start at 100 nanosecond, and then only then after the 90 nanosecond, it will change to another. It will change the output to another result. So if originally if from 000000 to 00001. Yes. So this is the simulation result for the clock period above 150 nanosecond. So the conclusion I made for in this part 2b, in order to work the whole circuit, my clock period needs to be exceed 150 nanosecond. Only then my combinational D flip-flop will work. So if my clock period is less than the propagation delay specified, which is 90 nanosecond and 150 nanosecond, my D flip-flop will not work. And so yeah, that's my conclusion for my part 2b. So for part 3, the students are required to design an implementation of 4-bit ALU unit, and we need to display the result on the 7-segment LED decoder here. So in this part 3, I had assigned all the 4 bits input values inside the codes, and the whole progress will be like automatic. It will counted automatically by the ALU unit, and then will be displayed on the 7-segment LED here. So this is the reset button. The first one button here is the reset button. So when the reset button is being pressed, the whole system will be stop working, and the 7-segment LED here doesn't shows anything. So if we turn off the reset button again, the system will start to work and display the result calculated by the ALU unit, and it will display the result on the 7-segment decoder here. So I turn on the reset button first. So for this one, LED 8, I used to indicate the 0 flag, and this LED 9, I used to indicate the carryover. So now I will display the result again, and then I will show the sample result sample results in this video part. So that's all for my part 3. Thank you.